Hello, we're back for some more exam questions on energy and work done. That's the main focus of all of this. We're starting by having to state the principle of conservation of energy. This is one of the more tricky or perhaps nuanced definitions that we give in classical mechanics. And that's really because there's this whole discussion that's gone on over years, really, of are we describing energy in as having different forms of energy. You've got gravitational potential energy, chemical potential energy, electrical potential energy, kinetic energy. Are these forms of energy? And I think quite reasonably people have become kind of wary of that because it overcomplicates things. Energy is just energy. So is that really the best way to start describing it all? Then they started moving into things like energy stores, but then I'm not a huge fan of those in all cases because not everything you really think of as being a store. Sometimes the energy is quite transient in where its location is. So I'm not a massive fan of either of those, particularly putting it in areas where we don't need it, like defining conservation of energy. So I prefer to go for the total energy of a closed system is constant. And okay, that requires you to know what we mean by a closed system, which is something we've discussed previously. Essentially, this is a system which is shut off from the world. It doesn't have external forces acting on it. It doesn't have matter going in and out. It doesn't have forces going in and out. So, yeah, I think that's better as a way of defining conservation of energy, at least at the moment. And then we can talk more specifically about where the energy is in certain scenarios. So I'm going to go with that one as a definition. Right now, we've got a glider on a horizontal frictionless track. What's in the text that isn't in the question? They've got the mass of the glider. One end of the string is fixed to the glider, other end to that mass, which they've given us. Held stationary at a height of 0.6 meters. Yep, that's there. Pulley is more than 0.6 meters away from the front of the glider, right? So the glider isn't going to hit the pulley before the mass hits the ground. When it's released, we've got this acceleration, constant acceleration of 2.8 meters per second squared. So that's new. And then when it hits the ground, it comes instantaneously to rest. Calculate the loss in potential energy of the mass as it falls through that distance. So that's going to be mgh is equal to 0.1 times 0.6 times g. Sticking that into the calculator, we got 0.5886. So that's 0.59 joules to two significant figures, which is what we're working on all of this. The glider starts from rest. Show that the velocity of the glider after traveling a distance of 0.6 meters is about 1.8 meters per second. So, okay, what are we getting up to here? Well, we got this acceleration here. So we can do our v squared equals u squared plus 2as. This is our conservation of energy Suvat equation. So our v squared, so v, well, u is starting from rest, so we don't have to worry about that. So v is going to be the square root of 2 times 2.8 times 0.6. All right, let's put all of that in just to make sure that's looking the same. So 1.2 times 2.8 equals that. So the square root of that is 1.83. That is 1.833, which equals 1.8 meters per second, again to two significant figures. So that's all fine. Nice that we got the same number. Calculate the kinetic energy of the glider. Okay, well, they're not expecting that much of us in this at the moment. So we've got kinetic energy is a half times 0.25 for the m multiplied by v squared. So we can just, well, we've still got that sitting in the calculator, the 3.36. So 3.36 times 0.25 times 0.5, 0.42 all in all. 0.42 joules. So yeah, not very much. I mean, you might get different numbers on this depending on what you've used. Oh, they said here, so it's interesting here where they've said at this velocity of 1.8 meters per second. So, I mean, it isn't really 1.8. I mean, it isn't. So it depends what you use on that. I mean, if we put all of that in again, I mean, let's see how much difference we would have got if we'd done 0.125 times 1.8 squared. Then you're going to get 0.41. So there's a little bit of leeway in this depending on which value we've used, whether we use that velocity or that velocity. What we mean by this velocity is a little open to debate. But yeah, I've gone back to the 1.833. Explain why the answer to B3. All right, so this amount of energy here is not the same as that amount of energy there. Right, well, we have, if you think of all of the, if this is our closed system, these two masses, so the glider and the mass moving around, it's frictionless, so we haven't got any external forces. You know, this is coming back to what we're meaning by a closed system. There's no energy going in and out of this system. Okay, when the mass hits the ground, things are then different. We've got an external force coming from the ground. Stops being a closed system then. But at the moment, you know, before, up until the instant that this mass hits the ground, there's no external force. We've got this closed system. So yeah, why aren't these things the same? Well, we've still got the kinetic energy of the mass. You know, this change in GPE that we've got because of this height drop, that's going into the kinetic energy of the glider and the kinetic energy of the mass. So we know what the kinetic energy of the mass is going to be now when it hits the ground, because it's going to be the difference. It's going to be what's left over, the difference between these two numbers. So, right. So, yeah, so quite an interesting question in some ways. The sums are very straightforward, but there's a lot of nuance in the ideas behind this, particularly this business of closed systems. So it's certainly something that you'd want to get your head around and understand when it comes to energy and where the energy is being transferred to, if anywhere at all. Right, now we're onto a roller coaster. For about the 20th time, we've got to start off by defining work done by a force. So work done by a force is the magnitude of the force multiplied by the distance moved in the direction of the force. We've had that a lot. B, figure 4.1 shows the side view of a roller coaster. Carriage and its passengers start at A. B, at the bottom of the ride, maximum speed is 20 meters per second. So we've got 20 meters per second down here. The vertical distance is 110 meters. They've marked that. The length of the track between A and B is 510 meters. Right, so that's a bit of extra that we've got there. The mass of the carriage and the passengers is 4,000 kilograms. So we've got 4,000 G going down. So it's just that 510 meters that's left kicking around. Complete the sentence below. As the carriage travels from A to B, something energy is transferred to something energy and heat. So that's going to be gravitational potential energy is transferred to kinetic energy and heat. So that's a nice starter. By considering this energy transfer from A to B, determine the average frictional force acting on the carriage and passengers between A and B. Right, so we've got for our conservation of energy equation that we've got here, so conservation of energy, we've got our GPE is going to the kinetic energy plus losses. So this is what we've said in this little bit that we just filled in the first part of the question. So that means that mgh equals a half mv squared plus the frictional force multiplied by the distance. So let's start putting all of this in, because this is our work done here. So losses is work done against friction. So that is our friction multiplied by the distance that we've moved. So our mass is, we've got 4,000 G multiplied by 110. So that's our GPE. That is going to be a half times 4,000 multiplied by 20 squared plus the friction that we're trying to work out multiplied by the distance that we've been acting against the friction, which is 510. So we got a lot to work out here. So F is going to be 4000 G times 110 minus, what's that, 2000 times 400 divided by 510. So that's quite a lot of friction that we're going to have here. So let's start tapping it all in and see what we get. 4000 times 9.81 times 110 minus, well, I didn't really need to do 2000 by 400 in here, but I have done, equals that, divided by 510 gives us 6894.9, which equals to our usual two significant figures that we'll do on this, 6.9 times 10 to the 3 newtons. Yeah, it's quite a straightforward question. That one is a nice one though. Right, they're back at us again. We're defining work done by a force. Work done by a force is the magnitude of the force multiplied by the distance moved in the direction of the force. Define power, rate of work done. Explain why the efficiency of a mechanical device can never be 100%, because there's always going to be some kind of loss, whether it's friction, going to heat, sound, whatever. There's always going to be some loss. You can't have a completely frictionless machine. Right, now we're on to the calculation bit. They're all sort of standard starters. A car has a total mass of 810 kilograms. Its speed changes from 0 to 30 meters per second in a time of 12 seconds. Calculate the change in the kinetic energy of the car. So delta kinetic energy, it starts with 0 and is going up to a half times 810 multiplied by v squared, which is 900. So what is that all in all? That is going to be 405 times 900 is 364,500. We seem to still be at two significant figures in these sort of things. So 3.6 times 10 to the 1, 2, 3, 4, 5 joules, because we've done energy. Calculate the average power generated by the car energy. Assume that the power generated is entirely used in increasing the kinetic energy of the car. Right, so we just need to divide this by 12, because the power is going to be the kinetic energy over the time, which is 30375, 3.0 times 10 to the 4 watts. Right, that's good. The actual efficiency of the car is 25%. The car takes 18 kilograms of petrol to fill its tank. The energy provided per kilogram of petrol is that. The drag force acting on the car at constant speed of 30 meters per second is that. Okay, calculate the work done against the drag force per second. So work done is force times distance. Force times distance. So our drag force is 500 newtons, and our we want work done per second, so that's quite handy. So work done per second is force times distance per second, so we can multiply by the 30 on that. So yeah, that's straightforward enough. We got 15 with 3 zeros, and that is watts. And then calculate the total distance the car can travel on a full tank of petrol when traveling at a constant speed of that. Okay, calculate the work done, total distance a car can travel on a full tank of petrol when traveling at that. Right, okay, so we've got our so the power of the engine was, is that what we worked out? Average power generated by the car engine. Assume that, well, that's while it's accelerating. Anyway, let's not worry about that at the moment. We've got per kilogram. So we've got 18 kilograms multiplied by 46 megajoules per kilogram. So that gives us our total energy. So total energy available, which is 18 times 46. 18 times 46 is 828 megajoules. So the total usable, or a total output energy, that's probably the best way to put it. Total output energy is going to be a quarter of that, because we got efficiency of 25%. So we've got 207 megajoules. So when we're traveling at this constant speed, this is how much that we're using here all of the time. So every second we're losing that amount of money. So the energy. So we're getting the total time is going to be the 2.07 times 10 to the 8 divided by 1.5 times 10 to the 4. So yeah, 2.07 divided by 1.5 is that, and that leaves us with a 10 to the 4. So we've got 1.38 times 10 to the 4 seconds. So if we multiply that by 30, then we're going to get meters. Multiplied by 30 gives us 4.1 times 10 to the 5 meters. Yeah, I mean, those sort of questions, they are quite difficult because we're having to go through so many different steps. So it's about taking it one step at a time on this. I mean, we've got this work done here, force per second. Of course, if we're moving at a constant speed, whatever we're putting in is going to be whatever's coming out. Yeah, we've got no acceleration. So the work that the engine is performing is going to be against the losses, and we know the rate of loss here. We know our energy per second that's having to be used up in order to maintain this speed of 30 meters per second. That's what we worked out. But then you just have to go through step at a time. Again, looking at the units, if you get stuck on any of these things of what to do, start saying, okay, well, we need energy. We've got energy per kilogram and we got kilograms. So let's multiply those together to get energy. That's good. We got this efficiency to get the energy that's available. If we've got, that's energy per second, and we've got energy available, where if you divide them, you're then going to get seconds, which is what we've done here. So the unit analysis is really useful. Then we've got seconds, and you multiply by meters per second, and it's going to bring us to meters. So if you get stuck on any of these things, just keep on looking at the units and what things can we multiply together to get the next thing in the chain. It's not really a case of, oh yeah, I can see exactly what I'm going to do as one big formula. As soon as you go into the question, you're just piecing it together bit by bit as you go along. So yeah, really nice question, that one, because it gets you thinking.